Hey, what's up guys? This is the Round Bottom Flask and welcome to the part 2 of the reactions of substituted benzenes. Before you proceed any further in this video, I suggest that you watch first the part 1 of this video wherein the link is somewhere located in the screen. As I have discussed in my previous video, substituents attached to the benzene ring affect both the reactivity of the ring towards electrophilic aromatic substitution and also affects as to where the next substituent will attach to. This graph here summarizes the effects of these substituents in both the reactivity and the direction or the directivity of the electrophilic aromatic substitution reaction. Now, I have told in my previous videos that electrophilic aromatic substitution has an added complexity when it's done on monosubstituted benzenes. Now, this complexity becomes magnified when disubstituted benzenes are involved. Let's take, for example, this transformation. Now, we know that this is an aromatic bromination, right? Okay, my pen is taking a while to load. Here it goes. However, both the substituents, the methyl group and the sulfonic acid group, will exert their own directing effects on the reaction. Now, the question is, since they will exert their own directly effects and obviously will point at different positions, at which carbon will the bromo group will attach to? Now, numerous studies on these reactions have been done, and thankfully, organic chemistry textbooks have summarized these findings rather into three comprehensible rules. By the way, shout out to McMurray, like you were my organic chemistry Bible when I was in college. You really helped me a lot to survive organic chemistry when I was in college. So the first one, the rules that I will be presenting in this video was actually an adaptation from McMurray's organic chemistry. Like I said, man, you were really a lifesaver. So the first one is substituents whose effects reinforce each other will yield a single product. Now, to elaborate, let's have an example of such disubstituted benzene. Now, this aromatic compound will undergo bromination reaction, obviously based on the reagents that is used. And the methyl group here, as we know, is an ortho and para directing activator. Now, the para position with respect to the methyl group is already occupied by this substituent here. Therefore, the only position left is the ortho position, which is here and here. Now, now this group here, which is for everyone's information, the acetyl group, this is called the acetyl group, is, we know, just like all carbonyl substituents, is a meta-directing deactivator. Now, since it is a meta-directing deactivator, the position of the next substitution will direct it to the meta position with respect to the acetyl group. And coincidentally, the meta position with respect to the acetyl group is also the same position which is ortho with respect to the methyl group, which is here indicated in the green arrows, and this one here. So obviously, it's pretty straightforward to where as to where the bromo group will attach in this substitution reaction. So since these two positions here are what we call as chemically equivalent, so therefore you attach the bromo group at either of this position, at either in this position, will give you a single product. Now, let's have another example here. So in this case, we have a starting material that has two ortho and para directing uh, activators as substituents. So namely the methoxy group, which is this one here. So we call this a methoxy group. And this is the amine or the amino group or the amino substituent. Now the methoxy group, obviously since it is an ortho and para directing activator, will direct here and here, since these are the positions which are ortho and para with respect to the methoxy group. Now the other ortho position is obviously occupied by the amino group. However, the amino group will point on the ortho and para position with respect to it. So the ortho and para position with respect to the amino group will be this one here, which is para with respect to the amino group, and this position here, which is ortho with respect to the amino group. Now, both substituents will direct the substitution reaction at different positions in the aromatic ring. So how do we decide which will be the major product that is formed? So the second rule is, if the directing effects of the two groups oppose each other, the more powerful activating group has a dominant influence. However, mixture products are often formed. Now, we know in our, let me go back to my slide here. We know in our reactivity that, what they call this, the amino group increases the reactivity of the aromatic ring more than the methoxy group, as shown here. Therefore, I'll go back to my slide again, just here. Therefore, the what they call this, the amino group is the more powerful activator than the methoxy group. So sorry, this is supposed to be methoxy group, so OCH3. Please disregard that. So it is a more powerful activator than the OCH3 group. So therefore, the amino group will have a greater influence as to where the next point of attachment will occur. So in this case, the bromo group will attach at this carbon and in this carbon respectively. Therefore, your major products will be two, wherein the bromo group will attach ortho with respect to the amino group, and the bromo group will attach para with respect to the amino group. So let's have another example here where one is an activator while one is a deactivator. I have indicated earlier that the methoxy group is an ortho and para directing activator, and obviously it will point to the ortho position, which is here, and to the para position with respect to the methoxy group, which is here. Now the nitro group, which is a meta-directing deactivator, will direct the substitution, as I've shown you here, in this carbon, and the other meta position is already occupied by the methoxy group. Since one of the substituents is an activator in accordance to the rule 2, the methoxy group will be the one that has the greater influence. So here, ortho and para directing activators will have a greater influence in the position of the next substitution reaction with the meta directing deactivators. Therefore, the sulfonic acid group will attach to the ortho and para position with respect to the methoxy group, as shown here. Now, you might have wondered that this position here is also or so with respect to the methoxy group. However, why is the next point substitution not here? Why is there no major product wherein the sulfonic acid group attached at this particular carbon? Now the answer is, again, the last rule is further substitution rarely occurs between the two groups in a meta-disubstituted compound because this site is too sterically hindered. So this site here, which is indicated by the red arrow, is hindered by these two substituents here in such that their electron clouds will act as some sort of a barrier in this carbon that will prevent or that will block the approach of the electrophile at this particular carbon. So therefore, you will only form these two major products, and this one product is not formed. So this is the end of my video, and here these are my not so I don't know if you consider that as prolific, but nonetheless these are my references. I hope you have learned something from this and find this a bit entertaining, I hope. If you have any questions regarding this topic, feel free to drop it in the comments below. Don't forget to like this video and please subscribe to my YouTube channel for more chemistry lectures video. So that's it guys, see you